Hello guys, today I'm gonna do a walkthrough of this project. We'll look at everything from setting up subscene to making procedural camera animations, shading, rendering in Karma, and also compositing in the COPS, which is built-in Houdini compositing network. This is not making from scratch, but I will go over this node by node, so feel free to skip around, and there will be time codes in the description as well. By the way, you can also get the project files from my Gumroad. Link will be in the description. Should mention that some of the assets might not be included with the file. Some of the textures, some imperfection textures as well. These are paid textures, but you can get the rocks from the bridge. This is the back. I'll also leave a link for this. If you go here and press go to files, you can get all of those files and just relink the textures with the image texture nodes here. And also this is the rocks that I used over here, as you can see. First thing first, let's talk about the RBD sourcing. So I import rocks. This is directly from the bridge. I didn't use Megascans plugins. I just loaded up this with the file node. I transformed them. I delete unnecessary attributes. I pack them using class attributes that they come with. So it's here. So next up, I did this little thing here just to visualize them. So I'm doing some transformations, colorization, and jittering them so I can see them piece by piece. So with that, I'm actually deleting this bigger rock here, the blast node. Then I'm using match axis. I'm just rotating this in the 90 degrees so they face the Z direction. This is used by the copy to points node. So copy to points internally uses Z direction as a facing forward. Then I calculate or generate the name attribute using connectivity. This will give every piece its own name attribute, which will be different for each piece, or you can actually use just enumerate. This will work the same way. Then I'm and it all goes to copy to points. So the target point for the copy, this is just a sphere. I just use mountain to just like distort it, give it the normals, point normals, scatter some points, jitter them. I use this scatter align sub in the attributes to existing point cloud mode and gave it the orient attribute. Then I use this attribute from pieces. What it does, it takes all of the pieces. They have this name attribute, as you can see, and it just assigns this name attribute back to points. So all the points have randomly shuffled this name attribute. So then we could use this in the copy to points as a piece attribute. So for each piece we'll have a different copy. You will see it later. This is let me just visualize the copy to points. So this wrangle is just brute forced p scales. So for each named primitive I give a different size. This is defined by these sliders. Then I do attribute randomize. I use this in the operation multiply, so I multiply the initial sizes with the random p scale. Then I use randomize orient. I use this inside sphere distribution, which gives us like a different randomized directions. And this font overlap is used by the RBD solver later on. This is just so there is no intersection. In the first frame, RBD solver will try to avoid any intersections. This is also, you can look it up, this is really useful integer attribute. And this is just to relax, so I try to avoid intersections as much as possible. Then I move them to the ground using the match size. I rename their name attribute to PID, and then I give it a new name attribute. Basically, with the RBD solver, we usually want string name, and then I just generate this string name using this line of code. Then it all starts a for loop. This for loop goes over every primitive. So this, because this is backed primitives, basically what it means that each piece is just one primitive because they're backed. They don't have like a individual polygons because it's all stored in the memory right now. So that's why I can use this over piece elements, just primitives, and it will iterate over each piece. And then I use compiled block and ticked this multi-thread when compiled, basically, so this whole setup is multi-threaded. I'm not sure if it gives like a speed benefits, but you know, just in case. So inside of this loop, I unpack this. I give it, I can transform this, convert this to the STF volume using VDP from polygons, reshaped it, so basically expanding it, then doing this VDP to spheres. Basically, I'm making like a collision representation for my pieces, so the solver you can use this later. Then I'm transferring the point attributes back to those pieces, deleting the color, and then packing it again. And as you can see, I'm transferring some of the attributes. So I have my PID, my name attribute back. And this is basically the collision representations. And that's it for the RBD sourcing. Next chapter, we'll look at the RBD solver itself. Let's talk about the RBD solver itself. Let's dive in. I'm gonna remove everything, just disable everything. This is RBD packed object. So basically, I'm taking my pieces from here. I'm just saying that they should use these guys as a collision, and then let's show guide geometry. And as you can see, those pieces basically like this, they have like a one name attribute. Every like sphere in this one piece have one name attribute, so they will be used as a one collision basically. So you have to tick this parameter, create convex hole per set of connected primitive. This is important. If you tick this, you will have a correct collisions. And I think that's pretty much it. There is some of the settings here. I ticked off compute mass. I think it looked better with my simulation. That's why I did this. And then in the rigid body solver, I just increased the slipping time and also used just a ground plane for the ground collisions. That's pretty much it. With the forces, I'm using the pop force to generate a global gravity. So I'm saying if frame is less than 722, our gravity will be like a 9.8, which is like a which is the default gravity force, you know, it's just defined. So they will fall, and after frame like 72, they will not have gravity at all. So then I'm doing this bed point gravity. So basically with this code, I'm saying that they have this activation offset. So this is when, after which frame actually the piece, this whole thing will start working. And then I'm saying that change per second, which basically means that how many seconds this the piece, this force will go over another rock element. So as you can see, after frame 72, you can see this piece, this one, it just it doesn't have gravity. Every other piece have, and after 4 seconds it falls, and some other piece just doesn't get gravity, as you can see with this one, for example. So this is done all this by this code. It's actually pretty easy. I'm just subtracting the activation offset from the frame, then divide this by C piece, which is like change per second, and I'm just saying that I want to clamp this basically from -1 to 100, and then I'm using this code here which says after frame 72, and if point number, which all of these pieces have, if it's not equals C now, which is the selected number, then gravity will be 9.8. So basically that's what's happening here. This is exactly the same thing. What I should have done is actually I was better off just to create one wrangle and then calculate everything here and then store this in the attribute, but I was too lazy. So what I did was I just brute force copied this code across all of these nodes, but basically they do the same thing. As you can see, they are even linked with this one, which is like the main one here. So this one does the same thing, but instead of like changing the gravity, this is just creating this group called exp. You can call this whatever you want. I just call this exp. I don't know what was the reasoning behind this. So this is the pop attract force. Basically what it does, it has this goal parameter, which means like it's like a point where the pieces will be attracted to, and here I'm saying that only this selected piece that we have will be attracted to this point. So what I have is like then the other one goes up, this one falls back down. So this is what it does. Then I'm doing some drag, then I'm doing some drag spin, so I don't have any spinning of the pieces, and I'm just giving them my custom pop spin. As you can see here, they are like nicely spinning over the Z direction, and these two drags is actually if you look at these pieces, they're jitter a lot, so I didn't want them to have any movement, so that's why I generated this X group, which what it does for this group, it applies a lot of drag and drag spin. So that's, as you can see, my pieces, they not move at all. So this is basically the RBD simulation. I fetch the points. So I don't want these pieces to be in my render, of course. So I just fetch the points here using create points to represent objects. And I'm caching them, loading them back, and using this transform pieces, which uses this name attribute that we had. And then I'm just transforming them pieces using this representation points. So basically this is what we have. And after this RBD simulations, we should talk about this affected attribute. So this affected attribute is like a main driving thing behind this whole effect. So basically what's happening is in order to convert this to Vellum simulations, I should know when I need to convert pieces to Vellum. So for this I use this selected attribute. So in this wrangle, what I'm saying that when the piece is like it's located like higher than this value. So I'm saying that if the y position of this piece is bigger than like a 1.75, which is somewhere right here, and also if the frame is bigger than 72, this is because, as you can see, if you remember, our pieces in the first frame is actually located above, so we don't want here them to be affected. We only want like a frame 72 after frame 72, and then we should say affected will be equal to 1. So this looks like this. As you can see, it goes up, it's affected, goes down, it's not, it's affected, it's not affected, it's not. So this is the main logic behind this stuff. And the next node is calculate seed. So what I'm hearing that if the piece is equals 1, which is which means that it's affected. Then let's give it ID based on its PT num. So for each affected piece, we will have like a different seed. For example, as you can see, this piece has seed of 0. Next one would have seed of 1, 2, and blah, and so on. So basically, this is also a necessary attribute later on. You will see why it's necessary. I will talk about this later. So then it gets here, and then I accumulate this affected attribute. Basically what it means that I want this attribute to not disappear after it's being affected, but to stay affected forever. So this is what it does. Inside, I'm just getting this affected attribute from the previous frame, and then I'm adding this back to the affected, and here I'm just clamping this affected to 1. So this is what this code is doing. In the next one, I freeze time in the last frame of this whole timeline, and I call this attribute affected all. Basically what it means that it just takes every piece. I think my Houdini viewport is bugged, so I'm just gonna say reset viewport. It should fix this. Okay, so I'm just freezing this, so all of my every piece that would be affected is actually have their attribute. Then I'm just transferring it back, as you can see, but I'm transferring this, copying this back, and I'm changing the name of it, so it will be called affected all. Here is very important one as well. Here I'm saying I'm colorizing this affected pieces to black. Then inside of this solver, I'm saying that, so I'm comparing the colors. What I want to know frame at which the pieces was affected. So I'm taking the current color, which is input 2 here. I'm taking the previous color, so I'm saying like a $F -1 in this time shift, and I'm just comparing them, saying if the color is less than previous color, then this is the affected frame. So I'm storing this into a FR attribute, and I'm just copying this. I'm again freezing the time because I want this to be evaluated across the whole timeline. So I'm just again clamping this and copying this back as a frame attribute. So next, in the next one, I'm saying leave the pieces that will be affected. So remember we did this affected all, and here I'm just saying if affected all is less than 1, then delete the point. And then so basically we'll just left with the pieces that will be affected. So next up, I just cast a frame from float to integer, because we want to have this as an integer attribute. As you can see, for example, this first piece will be affected at 109, as you can see here, for example, right? So 109, it's not affected, now it's affected. So this thing actually stores this frame attribute into this frame value into the attribute. This will be unnecessary for us as well. So next up, we go over this loop. Inside of this loop, I'm doing this by count, and I'm merging each iterations. Here I'm just saying that so we should run this loop. So basically, if we have like a 5 points, we should run this loop 5 times. So basically, this is what I'm saying. And for this, I used this spare input. I just dropped this over here, and I just said like endpoints -1. -1 means that it will refer to this spare input. Inside of this loop, so This is main one. I'm just passing this because I don't want to merge everything here, so I'm just passing this. I only want to merge this stream, and for this stream I'm saying that if point number of this piece is not equals to the current iteration value, then we should delete this piece. Then I'm saying we need to promote frame from point attribute to details. Then I'm saying that let's just freeze this piece on its affected frame. So for example, this is the last piece that it took, and its affected frame is 465. So that's when I should actually freeze this. And at the end, what we get is we get these pieces into like one location, and this location is actually when those pieces was affected. So this is what we used. I used this fixed time icon. So as you can see, we have like a time icon here. This could cause some issues, so that's why I use another shift. So next step, I'm copying back this frame attribute, the original one, from here back to the those pieces, and then I'm saying in this triangle those pieces should appear only on its activation frame. So for example, the first piece is 109 and it appears only on 109. Then I rename this name to piece name. This would be used later in the light beam generation. And then I'm saying unpack this geo, and this is all goes to the Vellum Sim. Before we talk about the Vellum sourcing, we must talk about this branch. Here I'm just moving in these rocks, then copying affected steel attribute from there. Then I'm removing this based on this attribute. So basically what I'm saying that when this piece gets affected, just remove it, and it goes all to the all pieces. Then I'm just renaming this name to piece name, unpacking those pieces, deleting the unnecessary attributes, creating this age. Its value will be equal to 0. This is, I think it's not important, but I still like to have it because they will because the Vellum pieces and RBD rock pieces will be merged. So in order to don't have any errors, I just like created this. I meant that they will have like a shared shader. So when importing the edge attribute into the shader, in order to not have any errors, I just made this attribute. Then I'm just coloring it in, and this null is actually used in the Karma as like a render source. So I'm sourcing my RBD rocks from this null. So yeah, this is like a render, already like a render rocks. In this branch, I'm just generating some lookup points. The same goes to this branch. We'll talk about this later. This is basically used throughout these cameras. They have all like a unified setup, but they all point to different pieces, different lookup points actually. So yeah, that's pretty much it. In the next chapter, let's talk about the Vellum sourcing. Talking about Vellum sourcing, in last chapter we stopped here to Vellum Sim, and here as you can see we have no geometry at all, but on their activation frames we have our geos here. I can't really use this geometry in my Vellum simulation, of course. So what I'm doing is I'm remeshing this, so they have like a uniform triangles. Then what I'm doing, I'm using this sphere generator, which generates this nice sphere with nice UVs. This is Labs sphere generator. And inside I'm just removing those nulls. So if you enable them, you have UVs like that. I didn't want that. I just want like a stacked UVs for each side of this sphere. This is basically to have like a tileable map applied to the sphere at the render time. Then I'm matching size, as you can see, with these rocks. Then I'm using this array project. This is quite easy. So inside, what I'm doing is I'm taking my sphere geometry, right? So in the first input we have our sphere geometry. I'm bringing this to the rocks here. So this is what I get. Then I'm blurring this. Then I'm again subdividing this, projecting this again, blurring, subdividing, projecting, blurring. That's pretty much it with this promote. So this is what gives us this nice quad geometry. It has some of this type of problems, but I think they are not really not really a problem for us. So the important part of this setup actually is, so this is not the rocks UVs, right? So they have their own UVs, and this is not that at all. So this is totally like a different UVs that we just generated. So what I'm saying that I want to move this UV to like a UV2, so just to new attribute. And then with this UV transfer, this is by the way labs UV transfer, I'm just transferring back our rock UVs back to this newly generated geometry. So this is quite important step. And then I'm copying back a piece name that we had here. This is also pretty important. Then the next step, what I'm doing is I'm giving this a rest attribute, so we can use like a procedural shaders. And here I'm saying that I just want to strip this piece name to just an integer attribute called UIT. I think this is used somewhere. I think later on I will see. And then it goes to the Vellum constraints. First one is cloth. You can see the settings here. I personally think that the settings of this node is not really matter at all, because this would be dependent on your scene totally, on your scene scale, like on your geometry. Actually, it's all totally dependent. So I think this settings you have to, like, if you want to recreate this, you have to figure out yourself what works best for you. And this is settings that work best in my case in this scene. Then I'm doing these two nulls, so geo and then our constraints. And the next chapter is actually, it goes to the Vellum simulation itself. And before we go into Vellum simulation, this is also like a branch over here. I'm taking this from copy frame, and then I'm saying that bring affected piece by piece. So what I'm saying here, I want to have like only, so basically I want to delete those pieces, everything that is not affected, and I want them to bring up like a piece by piece. For this I'm using this affected attribute, not affected still, but just affected. And here I'm saying that I want to promote this frame to detail using promotion method maximum. Why we want to bring them piece by piece is actually pretty simple. As you can see, first piece that will be bringed in is of course our first piece that starts with 109, and the frame is like 109. And of course this attribute promote would take the maximum value of all of these pieces. So in first frame this will be 109, but when the next piece comes in, this will be 181. Now of course we already will have like two pieces here, and then the biggest value of this frame attribute, we use this here, maximum. The maximum value of this frame attribute would be like a second piece. and then I'm just casting this and using this actually as an activation frame. So this will give to Vellum Sim information when to activate sourcing. This might be useless actually, because we still source our pieces step by step, but I still like to have it so the node inside is like not calculating unnecessary stuff for us. So yeah. So about Vellum Simulation, this is the DOP network. Let me just pause this. So the start frame is 96. I could use 109, but I just like to have a little pre-roll here. And then inside, what we have is, first of all, let's talk about collisions. So let's go to 109. So this is just ground plane, and this is rocks here. I'm just taking this from this render RBD rocks null. I talk about this here. So I'm taking there and using surface collisions. This is important, to be honest, because the surface collision is more stable. If we use like a volume collisions, what will happen when the piece gets deleted, this static object tries to recalculate the STF of the object, and when it's recalculated, what happens is that like a vellum geometry just pops. I'm not sure, I don't think it's a bug. I think that should happen. It just tries to recalculate, and like Vellum gives some errors. I'm not sure, to be honest. But the settings is pretty simple, but I just in surface representation I used edges. For my test it just worked better. So talking about the simulation itself, so in a Vellum object everything is default. In the Vellum sourcing, I'm using this pair input, which is referring to this activation frame that we did. And here I'm just saying in the activation emission type each frame, and here $F, which is current frame, when this equals our activation frame, only then we want to emit something here. So this is exactly what we need. Talking about the sources, I used a little bit of drag here. I created this age attribute. This is like when the piece just gets born. Let me just if the piece just gets burned, it gives this thing an age attribute, which just will be like growing from there, you know. So then I'm doing this Vellum constraint property. Here I'm just saying that a rest length scale of the pressure constraint, which is like a balloon constraints, would be equal to 5, and then with this age attribute, I'm saying if the age attributes gets to 2, like 2 seconds, this thing needs to grow twice. So this 5 will become 10. Then I'm doing this pop point, just to add some variations. And then this is gravity based on age. Again, I'm saying if this age attribute gets like, if piece lives like around 2 seconds, then this piece should have gravity and fall down. And if you want to see this in action, this is how it will look like. So as you can see, piece just pops in, and then it slowly goes down as the gravity rises. So this is the exact behavior that I wanted. So this is all I'm talking about, like a Vellum simulation. Then I'm just importing this, removing unnecessary attributes, deleting groups, and using this polysoup. This polysoup is again kind of unnecessary, but it actually saves you a lot of memory. So before you have like a 5 megabyte, and then after that you have like a 2. So of course when we have more pieces, this would actually be like a kind of optimization stuff for us. And then I'm caching this in. So after the caching this Vellum simulation, what I'm doing is I'm taking those pieces, I'm remapping their age to weight attribute. Then I'm blurring this based on this weight. So basically when piece just gets burned, it still has all of the like a rock geometry stuff, and slowly it gets just blurred. Then I'm giving this point normals, and using the same weight attribute, I'm just blurring those normals. So as you can see, just nicely gets blurred. Then I'm promoting this to vertex, deleting the unnecessary attributes. In this case, it's just the weight attribute, because we still have our original H. And then this is what gets used in the final render as a Vellum balloon pieces. In this chapter, let's talk about the procedural light beam. So this is the setup for this. It's quite easy, to be honest. So what we're doing here is just bringing in the Vellum pieces, which is this now, and then also the render RBD rocks. So we are merging them in. This is what we have. So here also I'm converting this from polysoup to polys. This is important. This is important for the procedural light beam. So this is the merge stuff. So what I'm doing here, I'm promoting this piece name to the primitive. Remember, I said this would be important for us, so that's why we using this here. Promoting this to primitives, and then I'm packing them using this piece name. So all of these pieces are now packed, and they have this nice piece name attribute. I'm promoting the piece name back to the points. I'm bringing in this unaffected, which is this now, if you remember, with our affected attribute. So I'm copying this from the source back to our pieces here. And then there's like a 2 branches, as you can see. This is like a 1 branch, and the first one is this one. So in here we are kind of using this ref end, which means that the last frame of our timeline, and then we divided this by 2, so kind of like a 240 frame. I'm using the bound node to generate the bounding box, and then what I'm doing is I'm using the sphere and then just using this bounding source as our like an input. I'm transferring this, increasing the uniform scale. I'm doing some clipping, and this I should explain. So remember, we have our backdrop, and this geometry piece would be used as a light beam source, so the light beams would go from there. So you should actually create this geo accordingly to your scene. So for example, if you want your light beams to start from the back, you should actually leave the back and delete this part here. So for this you can use actually these clip nodes. They are actually pretty useful. And then I'm scattering points, and remember we created this seed. So what I'm doing here, I'm adding a spare input here. I'm using this null as a spare input over here. Next, what I'm doing, I press this button, edit parameter interface, and then in here I just added the integer parameter here. This is this one called seed2. And so in the global seed, what I did was I said I want to use a detail attribute called seed that we generated before, and I want to take it from this spare input. This is -1, and I'm just additionally adding our seed over here, additional seed. So this is it, and for each affected piece, as you can see, it actually changes the input source. So this is exactly what we want. And then what I'm doing here, I'm actually copying, let's go to the next branch. With the next branch, what I'm doing here, I'm taking this packed primitives, packed pieces, I'm removing the geometries, and I'm keeping only affected one, so which means that I will leave only the piece that is affected right now. And also I'm using this as our focus point. I will talk about this later again. So I'm copying our age attribute back to this point. This is important thing here to tick. You have to tick this match by piece name. Then I'm remapping this. I'm creating this ramp. This is, I will again explain this a little bit later. So basically when the light just hits, as you can see, so let's go back a little bit. So when this beam hits the surface, it will just start to grow, and then when it's slow, and then it will slowly disappear, as you can see. So this is this age remapping, it's used for this. So actually I don't want to use these points directly because they don't have any attribute that we want to use later. So what I'm saying that I'm just taking this point from the affected piece, right? And I'm just saying that I want to copy the position from this scatter back to this point, and I will just move this to exact location as the scatter one. And I'm using this merge again. This is coming from this null to loop null, and this is when we generated our frame. And I'm again renaming the name to piece name and using this attribute copy in the same match by attribute parameter, transferring the frame. So this is basically our from PT, so where the beam would start, and this is the to PT where the beam needs to hit. So here what I'm doing, I'm generating the direction from the from PT to PT, and we end up with the normal here that points to the surface. So what I wanted to do, if we look at this null, as you can see, it's in the center, right? We don't want this to be in the center. We actually want this to be on the surface itself, not on the center of the bounding box. So for this, we generate this direction. We bring in the pieces from here. We unpack them. And again, of course, we keep only affected. And then we use this ray to project the points actually to the geometry. So this is used for this, and I use a little bit of lift just to, as you can see, I'm not sure, let me just increase the, I don't think you can see it, but here's our point that is projected using this directional attribute, and I'm doing some lifting, which is putting this point a little bit into the geometry. Then I'm moving this normal to original normal. So basically I'm removing the normal from this point and putting this into the another attribute called original normal. And this two attribute create, this is just giving them IDs. I don't think it's necessary, to be honest, but right now I thought that they are not necessary, but let's just leave them. So you can see that we have our 2 points. So we need to somehow merge them right now to create a line. But before we do that, you can see that they are moving. We don't want those lines actually to move, because this beam is not supposed to move. It's supposed to hit, stay a little bit, and then disappear. It's not supposed to move with the piece itself. So what I'm doing here, I'm taking the same loop that we did over here. I will not explain this again, but basically I'm doing the same thing here. I'm just freezing this on their frame attribute, and then I'm just copying this frozen position back to the original points, so thus we have just, you know, points that just stays in place. So this is our beam points. Then we use this connect to connect them together, and then we have our beam curve. So next up we remove unused attributes. We resample this curve. We use this h to p scale, so we say our p scale equals h, and then we make a geometry. And again, because we have this h attribute as a p scale, in the first frames it just slowly grows and then shrinks back because we did everything over with this node. And then here I'm saying if the p scale is equals 0, I want to delete all of the points, because if we don't, you have this just a curve. We don't want to have a curve here. So this is used in the render as a light beams. So next step is beam particles. So the way that I did this, I import this beam pt, which is here from this null. I import them back here using this object merge. I blast the first point, which happens to be the from point, and then I swag back this original normal. Remember, we moved this to this attribute called original n. So I'm swapping this back to normal. So we have this normal here pointing outwards of the surface. As you can see, this is used for the particles. So we're normalizing this, and also we are inverting this using this attribute adjust vector. So we're saying operation multiply -1, which inverts the vector, and also we'll take this make vectors unit length, which just normalize this. So this is our copy points. We use this peak. Remember, with the ray, we did this lift, so we just put this point a little bit inside of the surface, but now we want this back outside of it, as you can see here. And yeah, that's why we use this peak. And also remember to untick the recompute point normals. Then we're promoting the frame to detail, and also using this burst ID. Inside of this burst ID, we use this frame attribute to generate the random values. We use this offset to give this different seed, and this used as a burst ID. Burst ID again, this one is used by this Pyro burst source. So if you do this by default, right, Pyro burst source, this is used actually for generating some Houdini like pyro explosions and stuff, but I use this kind of in a manner just to create the particles. So what I did was I took this randomization by seed, and as a seed attribute I use this burst ID. Next up, I added a sphere input here. This is quite important as well, to be honest. You give this this null as a sphere input, and we use this as a start frame. So for the first piece, this will be like a start frame. Then you remember 180, this would be again used as a start frame. So this is changing every time. And if you do this just with just simple one frame like start, it will not start anytime the point changes. So that's why we need to use this detail attribute frame as our start frame. And then here is the other settings. I just play around with them, you know. It could not work for you, but it did work for me. So this is, again, as I said, totally dependent. And the burst step, I use a muzzle flash. Next step I'm jittering them a little bit. This is, again, I use all the time because the pop simulation causes this weird errors, not errors, but weird simulation motions if your particles are like located in a straight line. So that's why I always jitter them, and I delete unnecessary attributes. In this case, I just kept only the V attribute, and that's pretty much it. In the simulation itself, so what I did was, you can see the sub-steps, I just upped them to 2, but you can leave them to 1 again, but it could cause some weird issues. So for the tests, I always decrease this to 1, but for the final I just increase this to 2. Inside, I just generate some p scales. So when the points are born, you cannot see this with here because they are not visualized as a actual geometry, but rather just the points. But in the final rendering, what we will have is when they are just born. Where are the points? Okay, they are here. Come on. You can see it's not that fast, to be honest, but you know, doesn't really matter. So when they are burned, they will have p scale of 0. They will just grow, and then it just fade down again. Here I'm saying this is our global scale, global multiplier. Then I generate based on ID. So this is generating random sizes based on ID. Then using this ramp to generate this fading. Then I'm using this pop wind. Again, I'm using this age divided by life. So when the particles are just born, they will have a uniform, like an explosion thing. Then using this wind noises, it will just distort them, like, you know. And then this pop curve force, this is used to actually make particles follow wind. And here is the settings. So basically this is our curve, right? This is actually imported from the beam curve from over here. So it's not the final geo, but it's over here. And then inside, again, what I'm saying, that I want to have follow scale -1. What this means that it will follow the curve. This could be different depending on the winding, not on the point number of your curve. So in my case, as you can see, if I put this to 1, the points would go down. So that's why I did -1, so they go up. You can see the directions of the curves over here. The suction scales means that the scale of suction, basically like how particles would stick to this curve using, so like this. And then the orbit scales actually means that if our curve goes like this, and how many particles would be swirling around this curve. And the influence radius is just this, like how far, basically this is the affecting area of this curve. And then again, a little bit of pop drag, and everything else is just by default. And the important part as well here is in the pop source, we want to use this activation frame. This is actually really important because otherwise you will have infinitely spawning particles, and there is some change life variance, life expectancy. And also I bring in the velocity that we kept, and then add some variation to this. That's pretty much for the simulation. Next step we do is we generate this lifespan attribute just to colorize them. Next up, I add a random attribute. This is for the rendering part. I will use this in the shader. And most important one, actually, you can see we have a lot of intersections. This could cause some issues in the rendering. So what I'm doing here, I'm bringing in this merged, so the merged rocks and then the merged vellum pieces. This is from here, if you remember. And then I'm converting this to the polygons using the VDB reshape to expand them, and using convert VDB to convert this from STF to fog. So inside of this, what I'm saying, you can see this if I do this lid spheres. As you can see, there was some intersections, but after that I just removed them. So what we do here is we sample this volume, we invert this, and we just multiply our p scale with this inverted fog volume. So basically what it's saying that inside of this fog, those particle scales should equal to 0, and then we output this. This bit of code is used to delete those points because right now they are not deleted, but I ended up not using this because it also can cause some issues with the rendering in Karma. With Redshift it was okay, to be honest. So you might want to enable this. Here I'm just comparing, saying if the p scale equals 0, use ID to remove the points. As you can see, we don't have any points, but again, in this case I did not use them. And then I'm deleting the unused attributes, deleting unused groups, and this is what goes to the render as a particles. And also, again, as I said, they just, for every piece, this burst is actually different, you know, so the motion is actually different for each piece, which is kind of pretty cool thing. And as I said, you can see they are slowly fade down. They are not just like disappearing in the air. So this is the important part as well. This is it for the particles. Before we dive into the karma, let's talk about the camera animations. In the scene itself, this is the main camera. As you can see, it actually follows these pieces kind of in nice motion. It doesn't like go to one to the other. It just slowly, smoothly looks at it. And also we have this focus point. Let's start with this. Remember, we had this focus point over here when we are keeping the affected ones. So I'm using this null as a spare input, and here I'm just setting the positions of this focus point or focus null to this point positions. This is the expression, you can use them. And in the camera, in the focus distance, I'm saying this is the expression actually used to face, to like a calculate distance from the camera to this null. To be honest, I'm not really sure about this expression. I don't know how it works, but this is what I found on the internet, and this is just works perfectly fine, because I think this is like old expression stuff. I'm not really familiar with it, to be honest, but this works just perfectly. Talking about the camera setup itself, let's dive inside because we are using chops. So as you can see, there is no keyframes. First thing what you do is you set up your like a basic camera, you know. So this is what worked for me. And then let's dive inside. Here I'm getting this camera's position. As you can see, it's not moving at all. Then I'm giving this a little bit of shake. As you can see inside, what I'm saying, I'm using this unified noise static. For my taste, this noise type worked best for this kind of stuff. As a position input, I'm using this C input here. Basically, this is channel number of current channel. So this channel warp, we are scoping the only rotational axis. With this node, we take in all of our channels, which is translations, rotations, and scaling. This is there. In the case of camera, we don't have scale, but it still gets it, because I think internally this still has some scale. And what I'm saying here, I want this camera shake only on the rotational parameters. So this is there, and then inside again, this is C, back to the C attribute, not attribute input. Basically, this C variable would be different for the each channel that we scope over here. So for the each Rx, Ry, Rz, this would be different. So that's why we have different noise. And then we use this T variable. This is just a time. We divide this. This is like a speed, and we put this straight to the offset. This is the overall the amplitude multiply, and then we add this to the V. This is current sample value that we have for example 240, which means that this sample value would be equal to this values over here. In this case, of course, they are not different at all, so we just add whole of this stuff back to the current value of the channels, and we output them. So that's why we have scale. So this look at constraints, what I'm still doing is I'm using this geometry chop. I'm taking this look at point. Remember, we did this look at point over here. So basically what we did here, we again leave only the current piece. We leave only the geometry, we leave only point, we delete geometry, and we also, just in case, delete all of the attributes. So this is the look at point hour, and here inside of this we say let's take this sub. Also this extend right, I use this as a mirror just in case. Method, we use animated, so it actually brings in all of those stuff. You can see this is actually the movement of our point. You can see this. You can see this here. This is the movement of this point. So we just straightly imported the whole movement. And what we do, we shift this. This shift is by half second. This is actually used, you know, our camera, when it looks at the object, we want to focus to this object before the beam hits it, because we kind of have like a pre-roll kind of thing. So that's why I shift this, and I used this smooth. This smooth is quite important one, because this what gives this nice smooth motion. And we use this constraint look at to actually scope. Again, we scope only the rotation channels, and we say the rotation should look at this null. And this is, as you can see, this is quite strong for my taste, so that's why I use this blend. This blend takes the first input, it takes as a amount, blending amount. You can use just a channel called blend. The first value would be your blend, and I blend this between the original one and this look at one. I just blend them together, so that's why I have this nice motion. And all of this stuff actually goes the same thing for all of the other cameras. As you can see, The same thing actually. I just used like a different nulls for this. For some of them you can see I didn't even use anything. I just used just camera shake, you know, but on the end, you know, they just refer to different nulls, but inside it's just the same. So that was it for the camera animations. Let's dive into the karma. So I'm gonna be doing first of all overview, then I will talk about the shaders. So basically what I'm doing here, the blue nodes here is just importing different sub elements. As you can see here, I'm doing the sub import and I'm referring directly to this render nulls that I used. This goes for everything here. And when you're working with the karma, you should always look at your scene graph tree. This is actually pretty good stuff here, just to, you know, visualize your scene in this like a graph context. What different in this nodes is this import prefix. So if you just do sub import, you have this $OS. What I wanted to have them inside of this group called geometry. So that's why, as you can see, you have this stuff here. You know, you have your geometry and you have your all of your different stuff. And then this is materials. Basically here I'm assigning the materials over here. Again, as I said, we'll talk about this later. Let's go next. So here we have our null. This is just the geometry and materials. And then this is the different shots that you see in this layer motion piece. So I set the RAM this way. Basically what I'm doing here, I'm importing the lights. Yes, I had a couple of lights, couple of redshift lights actually. This is used from the like redshift renderer. This is not included with the file. If you want, actually I can do redshift version as well. Just hit me in the comments. Basically this is like a key light and this is just little fill light over here. So I'm importing them here. Let's switch to karma. Right, so let it give a little bit of time. There you go, this is the karma. As you can see, those lights are, let me just disable the visualization stuff. This light is really like a lame. It's not like, it just doesn't highlight anything. So what I did, I dropped down the edit light, right? And then in this edit light, again, in this scene import, what I'm saying that I want to import lights. I selected these two lights and I made this group called lights. So that's why I have this in the scene graph tree, I have this group called lights. And then I'm just dropping this key light into this edit light and then changing the uniform scale, making this light a little bit bigger, just so I have more nicer, more soft shadows in here. Then I'm adding the new lights. This is the shared light between all of the scenes. So this is just the backlighting, just to give some rim light. And then I'm using this light linker. I'm selecting this rim light and saying that inside of geometry, I don't want this light to affect my backdrop. So I'm dropping this into the second slot here. And thus I don't have rim light affecting the backdrop. So this is the lights turning on. As you can see in the final animation, you actually have them like to flickering, turning on. This is what this thing does. So I'm saying that I want to multiply the intensity channels of the lights using this chop. I will not go over to this chop, but just to briefly go, what I'm doing here, I have this light which is just animated, this input from 0 to 1. I'm inverting its range. I'm limiting this. This actually does nothing, I think. You can disable this. And I'm using this noise, and I'm just multiplying this channel with that noise, and again I'm multiplying back with the basic light animation back to this, and in the end we again use this math, and what we say is I want the length of this chop to be like a based so basically I'm saying that I don't want this noise to go all over the place. I just want the noise to just add on top of the original light. So basically this animation, it just starts from 0 and it just goes all the way up, but when we add the noise, what we have is we have this nice flickering, as you can see. And then we just limit this to the ones, and this is used for all of the other lights as well. So this is lights turning on. Then I'm importing the main camera. This is the hero shot. I'm importing the main camera, and let's go a little bit further. There you go. And then I'm editing this a little bit. I'm just changing the f-stop so the depth of field is more shallow, and this is the Karma render settings. What's important here, of course, I'm switching to the XPU here. As you can see, it renders quite fast. And then inside of camera effects, I'm using the velocity blur here just to have some velocity on my particles. And then also I'm outputting the AOV called direct emission. So this is just my emission here. And also most important thing is to switch from the light tree to uniform. If you don't, you will have some really bad artifacts on your render. This doesn't really give you that much speed increase in case of this scene, but this thing is actually, I think, is used when you have like a ton of lights and you just want to do like a single shot. So that's why you can use this in these situations, but I always switch this back to uniform. I haven't seen any speed improvements using the light tree, but it does give you like a really bad artifacts on your render. Unfortunately, I can't show you them right now because I deleted those files, but if I thought I would do a tutorial, I would definitely save them. And the same thing actually goes for the other shots as well. Just importing lights, doing some edits. Same thing goes with this one. Just different cameras, different lights. The settings are the same actually throughout the scene. That's pretty much for the Karma. I haven't changed anything else. And let's talk about the materials in the next chapter. So with the materials, so let me just add some dome lights. So we just have like a basic lighting here. So what I have in here, first of all, it's just a backdrop material. So this is the Grayscale Gorilla materials used for these sheets, as you can see. And the pattern is also I grabbed somewhere in the internet, I don't really remember. If we visualize them, this is the pattern, and then this is our let it just cook. This is our kind of like a weave texture thing. Let's put this back. So what I'm doing is I'm taking the diffuse map, I'm taking the luminance, and I'm multiplying this over this grid. So in the end we have something like this. let it cook. You know, we just multiply this. I mean, it's not visible here, to be honest. Let me just increase the, there you go. You can see we're just multiplying this grid pattern with this diffuse texture. This is the roughness. Again, just remapping the lowest value here. And then this is the normal, just putting down this to the normal map, changing the scale. And this is the output for the backdrop. This is just these RBD rocks here, these ones, not the Vellum ones, but the regular ones. And in here I'm saying I'm taking the materials. Remember I showed you where to grab this rock, and this is basically this rock texture. The important thing for me was to have those rocks as a one pack, because if you have them as a one pack, what you get is you get like a one unified texture. So this was the important part. Here I'm doing the texture color corrections, piping this to the roughness, and this is just like a basic stuff. And I should mention that for this project I'm using the MaterialX. I mean, I always use MaterialX with the Karma. And those subnetworks actually are Karma MaterialX subnetworks, not the MaterialX subnet. Not this one, but the Karma one. Because with the Karma, you have some additional nodes, some additional USD nodes as a USD UV texture, primvar reader. This is for your attribute, importing your attributes custom. So talking about the Vellum rocks, as you can see, I have this global control thing. This is just going through all of those subnetworks, and this is just to have a global control for the colors. So this actually changes the beam, particles, and then the RBD vellum balloon cloth texture as well. This is that. And then this is the emission amplitude for the beam and the particles. They all go straight to the Vellum rocks. And inside there is some stuff, as you can see. The green ones actually is the rock materials. And what I'm doing is I'm using this age attribute. This is like a primvar reader, so float age attribute. I'm remapping this age attribute, and then I'm using this to blend each channel. So why I'm doing this like that is because with the Karma XPU, you don't have ability to blend between the BSDF surface materials. So you can't really blend those materials with the XPU. So that's why I'm blending each channel. So I have my color, which goes from here, you know, and I'm using this edge attribute to blend between the rock color and then the you can see if we go 109, you can see here this actually quite strange behavior. This might be because of dome lights. Actually, it's not strange. I might need to relink those. No, they are the same. Maybe color correction different. Strange. Let's just figure out this together. So, oh shit, of course you have to use, it's not in the default but in the texture coordinates. They should fix it. Come on. Actually, it did not fix it at all. Let me just use surface on it. What's happening? Oh, of course, I need to use this as a color, so that's why it changed. I think I was fiddling around with this material before starting to record this, and that's why I just fucked this up a little bit, but I know. And it's fine for the other maps. Yeah, of course it's fine for the other maps, and it should be fine. Yeah, it should be fine here as well. Yeah, so that was the problem. I'm sorry for this, but so basically we are just, you know, blending between those materials. As you can see, the same thing goes for this. So I'm blending the roughness map with this imperfection maps as well. This is, I think, is Cornelius Demrich imperfection map, and I'm just remapping this a little bit, and then using this MaterialX mix to just mix between those two materials. And the same thing for the normal map. Remember, we did create the UV2 attribute, so this is when we actually use this. As you can see, for the cloth bump texture, as you can see, this is the cloth bump texture for this one. And then for the imperfection maps, we are using a different UV set, and then we can import this using this, again, Primvar reader. So that's pretty much it. You know, we use this height to normal, which creates a normal map from the height, and then we use this mix normals, no, MaterialX mix, to mix between those two normals, and then we output this to MaterialX normal map node. So basically this is it for your balloons texture. For the particles, what I do is I use this incoming color in incoming intensity. So what I did was I used this color correct. I bring in the random value that we created before. I just remap this, and if you look closely, we can see that we have a not just one color in the particles, but different ones. So this is what it does. It just changes the hue randomly a little bit. This one is used to change the saturation. So this lifespan attribute, when they are just burned, it goes from 0 to 1. So when they are just burned, the particles should be more white, and then they are goes to its original color. And this one is used just for the emission. So I take the same lifespan, I put this to output a high, this overall intensity, and that's what I used for the particles. For the light beams, the setup is pretty much the same. Age attribute, multiply this overall incoming intensity, and then use this as a emission intensity, and use the color as a emission color. So that's it for the shader building. And then what you can do is you can specify your output picture path, specify your camera, and then drop down USD render up, and then you just render out your images. And in the next chapter we will be compositing them using the cups. So when we are done with our karma stuff, we actually we output all of the sequences using this render up. Again, as I said, we take the direct emission pass, and let's dive inside the compositing. So the first node is file node. If we switch to the composite view here, this is what we get, like a final render. You can do denoise if you have noise, but make sure you have those two AOVs here, normal and albedo. Again, you can get them from here. So this will be your albedo, and then this will be your N, smooth normal, and then inside you can just like, it will specify them automatically, but in this case I didn't output them because I don't really have much noise in there. You can use this noise without, you can just use this denoise without those planes, but then it will have less accurate results. So there's two branches, as you can see. In the first one we delete everything but the C. C is like a RGB channel inside of Houdini, which is delete everything but the C. In here we do the same thing, but for the direct emission pass that we outputted, we rename this pass to the C, and we use Luma key. Luma key, based on this max luminance value, generates the alpha channel and actually masks out the brightest parts of your image. Then it will blur them, and then it goes to this beam distortion VOP. This is the same like a point VOP, but it works with the images, in this case inside of the COP network. Inside, what we're doing is we're using some masks, some turbulent mask, and we use the mask from the second input as well, just to distort the channel to have this nice beam, like a chromatic separations on exactly this beam channel, and also it's also animating as well. So inside, first what we do is we import mask from second plate, which is this one. We get the channels using cop input and using our UV plate, so basically like a sampling. So it starts from 0 here to 1 here, and the same one goes for the y-axis. This is basically like your position of your geometry, so to speak. And then we take the C channel from the second input, which is this one, right? And then we put this through luminance, and we use the smooth. The smooth is actually like a fit range, but what it has is it's does the remapping not in a linear fashion like fit range does, but it actually uses like a bezier, more smooth curves to do so. So in the end, what you will get out of this is you will get your mask imported in here and remapped as well. And next step, what you do, I will generate a radial mask. What we need this for is we need this to actually to mask out the edges of our footage, but I use this switch. This switch is actually like a turning on and off, and as you can see at the end, I didn't use this, but you can use them if you don't want to be, like for example, in upper edges not be affected. You can use this mask as well. Next up, what we do is we generate some noise. This is the noise. This is for distorting the images, distort the C plane here, and as you can see, it's linked to the animation speed, which goes into the third component, because we are working in the 2 dimensions here, and if you put the time into the third component, you will get animated noise, as you can see. Here's the settings. So again, we're also multiplying this with this constant called noise frequency, so you can control the frequency of the noise. This all gets to the masks, so we apply mask to this noise. We end up with something like this, and then we multiply this with the overall amplitude here, and we generate a vector of this. Then we take our original like a UV channel, and we distort this using this noise. We add this noise to it. You will see nothing here because the values are so small, but it will be visible in the footage itself. So we don't do anything for the green channel, it just gets outputted here. But for the blue channel, we do the same thing, but instead of adding the noise, we subtract it, so it goes the other direction. And at the end, what you get, if you, again, this is just sampling the channels. We're using the position. In case of red and blue channel, we distort those positions. In case of the green channel, we just directly output them. And at the end, you will get something like this, which is, it will be like nicely distorted here. Again, using the same mask, we blur a little bit here, just to have like a more smooth transitions. And the next thing what we do, we take the direct emission and we add this on top of the footage. This is actually done to make the luminance values of the beam more obvious, kind of, so to speak. Basically, they make it more brighter by adding them back to the geometry. This is done in order to mask them more correctly. You will see it later for the glove part. So with the saturation here, we just desaturate the image a little bit, and then we extract the luma using this swap. In here, same thing, getting our RGB channels, getting the luminance, using this smooth, as I commented here, almost same as fit range, but in this case we remat with kind of Bezier curve. We multiply our original color and we output this back, so you have just beam here. Then we blur it a little bit, and this is the important part. As you can see, I have a lot of blurs. Unfortunately, we don't have a for loop inside of COPS, so we have to do this manually. But in here, I set it up those two parameters. You can also set it up like this, just drop down, rename parameters. But basically what I'm saying here, I have this another blur, right? I'm blurring this a little bit, then doing another blur. In here, I'm saying this blur's size multiplied with the exponential roll-off, and then multiplied with the additional multiplier. So this is what I have. As you can see, you can control the roll-off, you can control additional multiplier as well. And in the next blur, I'm saying let's take this blur's size and just multiply this by 2.25. You can set whatever value you want, but I find that this works fine for me. And the same goes for this one. It takes this blur's size, again multiplies it, and so on and so forth. So in the end, we have something like this. As you can see, nicely exponential glow. This brightness, basically what is happening, I have a some expression here, and basically for the each node, as you can see, 1 divided by 2, so this is the second blur, and plus some value here as well. And the same thing goes this 1 divided by 3, this is the third one, fourth, fifth, sixth. So basically for each blur, as it goes down the chain, the brightness will be less and less. This is also one of the important key stuff for the exponential blur. Then we do reduce some brightness of this glow, remove the alpha channel, and then add back this glow. And as you can see, you have a very nice glow here. And also using this HSV, you can control the You can make this blur just white, or you can make this fully saturated as well. I just found that 0.75 works just fine for me. And then you can use these roll-offs to control the glow better. Next step, I'm just cropping this, because for now, actually you can see our bounds are really big because of the glows. What we do, so basically you can actually see only this part, but if you go down the chain and start doing some operations, it will actually apply all of those operations in these areas as well. We don't want that, so that's why we use crop, and we crop just our image. This is the overall chromatic aberration, as you can see on the rocks, and also distorts an image. If you dive inside, this is from CG Wiki. He had some on his site. He had some chromatic aberration. This is based on his work, but I actually use just WOPs to do so, and also it's a little bit more optimized in my mind actually. So this is the amount, as you can see. This is the amount of the distortion. This is actually works not that great because it has some problems if you go too much with it, but if you just have just a bit, it works just perfectly fine. This is the same gradient radial UV map to distort the original plane that we have here, and then this is for the chromatic aberration of those channels. So basically, I'm taking this distorted UV, I'm multiplying this by 0.5. This is done to have more centered UVs, and then for each channel, as you can see, for the red channel, I'm subtracting this value. For the blue channel, I'm adding this value, and the green is the original. So at the end, we get this chromatic aberration. Basically the same process as for the heat distortion over here. And then we do some sharpening, then we do some color correction, we add some grains, and then we again crop bounce, and this is it. This is your cops. And the thing is that I'm working in ACES, I'm sorry. And so if I output this directly using this file output, the color management, of course, would not be correct, because we are viewing the image as an sRGB. So we need to do this thing. So here I'm saying that let's take the C channel, let's take the color channel, let's use this OCI transform from space access CG to sRGB using this power. This is basically like a gamma, so 2.2, and then let's output this. So when we output this sequence, right, we will have we'll use this convert to image color space, and then at the end we'll have a correct color space. So that was it for the COPS compositing. Next up, I will show you how to output a video from those sequences. So in order to output the video from the sequences, we are not going to use this ROP file output, because this thing only can output the EXR files. I mean, if it works for you, that's fine, but I wanted to get like a final video output from this, and to do so we need to use a FFmpeg, and this can be done inside of the dot network. So using this ROP composite, we take our cop null here, we output a picture, we specify the path, and then specify our frame range. Cache mode, I put this into write files, so this will cache out our sequences inside of this folder in my case. it will wait till it's done, till it gathered all the sequences, and then it will put down the FFmpeg encode. So what's the difference here? Again, the cache mode write files, a frame list file. I saved this inside of this folder. This is actually important because by default with this, it saved this into the temporary direction. But if you have your main Houdini file, if it's not located into the same directory as your Houdini installation, it will give you errors. So that's why I put down this heap path. You can just copy and paste this. It will work with every heap file. Basically, it uses the Houdini heap files direction, creates a new folder, and then a temporary sequences, and then you creates this frame list. This needs to be created in order for this node to work. And then output a file path, basically where to output your MP4. And there's something changed with this. By default, if you output this and change this frame list file, it will work fine for you, but the bitrate will be really bad. So you can use custom commands in here. And I know a little bit of FFmpeg, so what I did was everything else I unticked. I ticked only those 3 options, and then what I said after this FPS thing, you just type backslash slash preset very slow. This is for the preset. This is more kind of accurate, and this is the quality. So basically 0 means it will be lossless, and the file sizes are actually not that big, 165 megabytes. But if we want to have something, for example, to like upload to Discord, you can just stick basically to the defaults. It still give you the fine result. You just untick this thing, and then that's pretty much it. If you output this like this, it will give you more compressed image. So yeah, that's pretty much it for the video. These 2 stuff is I'm just taking those sequences that we output into temporary direction here, and I'm just deleting them, right? And I'm taking them, and here I'm just like removing those files. So that's pretty much it, because I don't want to save sequences, I just want to save my file. So that's why I'm using those 2 nodes here. So this video turned out to be very long. If you have any questions, you can ask me in the comment section. And as I said, the project file will be available on Gumroad. Link will be in the description. I think will be like a $2. I don't think it's much for what you're getting. You know, you can play around with this setup, create your own stuff, and as I said, if you have any question, just leave them in the comments. Thank you.